Since the next topic that we're going to be talking about is moisture in the atmosphere, it's very important that we understand how the phase changes work. And what might be a little bit different this year is not only do we want to know is the phase change going from a solid to a liquid or a liquid to a gas or any of those combinations, but we also want to try to focus on how much energy is involved in that phase change. And we have a diagram and a reference tables. I'm kind of highlighting it up here at the top that says properties of water. It's right on the front page of your reference tables. And it gives you the amount of energy that is involved in each of these phase changes. So what we want to do is just kind of run through the phase changes quickly together. And what we want to focus on this time is, does the water have to gain or lose or release energy in order for that phase change to happen? So let's start with the first one. The first one on the list up here is melting. And obviously, if something's melting, in the case of water, it's going from a solid, which is ice, and we're turning it into a liquid. So think for a second. If I want to go from a solid to a liquid, does that water or that ice have to gain energy or lose energy? Hopefully you said it has to gain it, because you have to heat the ice up in order for it to go and become a liquid. Now, how much energy do we have to put into it? Well, if we look on the chart, it tells us that the energy gained during melting is 334 joules for every gram of water that we have. Remember, a joule is our unit of heat energy. So that's the first one we're going to take a peek at. And then obviously the opposite of melting is freezing. So if we pour the water into an ice tray, we put it into a freezer to cool it down, well, then we're going to be having to release energy. The energy that was absorbed by that water to go to a liquid now has to be given off. And it's going to now have to slow those molecules down so that they bind together as ice. And to do that, it's going to have to release 334 joules for every gram. So it's the same amount of energy. The question is, in melting, you're absorbing that energy, and in freezing, you're releasing that same amount of energy. We call this latent heat. This is the amount of heat that is stored within the water molecules. In the case of going from solid ice to a liquid, what you're really doing by putting that energy into the ice is making the molecules start to move faster, so they turn into the liquid state. When we freeze it back into ice, those molecules are losing energy, so they're starting to slow down, and eventually they form into an ice cube. Then if we take a look at the next one up here, we have vaporization. Vaporization is just another word for evaporation. It has the word vapor in it, think of a gas. And in this case, if we had liquid water and we heat it up, if we add energy to that water, the water's gaining the energy, it will turn into water vapor, which is the invisible gas that's mixed in with all the other gases in the air right now. And to do that, we have to add 2,260 joules for every gram. So it takes a lot more energy to get from the liquid phase into the gas phase. And that's because the molecules have to start moving a lot faster to go from a liquid into a gas. The opposite of evaporation or vaporization, whichever word you choose to use, is condensation. And that's when the water goes from a gas back to a liquid. And to do that, it has to release that latent heat energy that it absorbed. It has to release 2,260 joules for every gram of vapor that there is to turn it back into liquid water. So that's the focus we want to have right now, is on the energy change. And we're going to switch to a different sheet to do a little bit of practice with that.